Welcome to the Everyday Journal Club. I'm Hope, a biologist with 15 years of research experience, now fortunate to be working in a Nobel Prize winning lab. This channel has three main goals. One, to help you stay effortlessly updated on the latest scientific breakthroughs. No paywalls, no jargon overload. Two, to build a supportive community where we can exchange the most valuable experience based research advice. Three, to share valuable strategies and concrete examples on how to achieve meaningful scientific breakthroughs. Once we reach 1,000 subscribers, I'll begin releasing content focused on the third goal. Let's go! Let's make great science together.
Okay, so let's dive right in.
Okay, let's dive into something really foundational today. Picture this. Scientists trying to figure out proteins, these crucial molecules of life. For ages, the mental image was, well, kind of fuzzy, right? Maybe like messy, random coils or just blobs.
Yeah, unstructured blobs was definitely a thought. But then, bam, 1958, a paper lands, and suddenly, the first time we see a protein's 3D structure near atomic detail, it's not a blob at all.
Not even close. It was this amazing, elegant bundle of like spirals, helices. It just flipped the script entirely on what proteins look like. It's like finding out a messy pile of cables is actually this incredibly intricate, perfectly wired circuit board once you get a clear look.
Exactly. And this paper, the one in Nature on myoglobin structure from X-ray analysis, it's huge. People talk about it in the same way they talk about discovering the DNA double helix.
Yeah.
Really that level of impact.
Absolutely fundamental. So that's our mission for this deep dive. We're using that landmark 58 paper plus some related materials as our guide. We want to explore that massive puzzle. How do you see a molecule? Look at the clever methods they came up with, what that first structure actually showed us, and, why it still matters so much today.
Okay, so let's rewind a bit. What did we actually know about proteins back then, say in the early 50s, before this breakthrough?
Well, they knew the basics. Thanks to people like Frederick Sanger mapping out insulin, they knew proteins were these long chains of amino acids. That's the primary structure, like beads on a string.
Right, the sequence. And they also had ideas about local patterns, the secondary structure. Pauling and Corey had predicted things like alpha-helices and pleated sheets.
Yeah, and they'd seen those structures in certain proteins, like fibrous ones, keratin in your hair, silk, stuff like that.
But that's the key point, fibrous proteins. They're often quite repetitive, structurally simpler in a way. The big question mark was over the globular proteins.
The workhorses, enzymes, transporters,
Ah,
the ones folding into compact shapes.
exactly. How does that linear string fold up into a specific functional 3D shape? What did that overall shape, the tertiary structure, even look like? Nobody knew. It was a complete mystery.
And everyone kind of knew instinctively that shape had to be critical for function, right? An enzyme needs a perfectly shaped pocket. A receptor needs a specific docking site.
Absolutely. Structure equals function was the idea.
Yeah.
But without seeing the structure, understanding how these things worked at a molecular level was just guesswork.
So they had this tool, X-ray diffraction. What was the deal with that?
Well, back in the 30s, Bernal and Hodgkin showed something amazing. You could get protein crystals, shine X-rays through them, and get these diffraction patterns of spots on film.
Okay, so the patterns held the information.
They did. In theory, that pattern contained everything needed to figure out the 3D arrangement of atoms in the protein, but
There's always a but.
there was a huge but. They could measure the intensity of those spots, how bright they were. That gives you the amplitude of the scattered X-ray waves.
Right.
But to reconstruct the 3D image, you also need the phase of each wave, basically where each wave started in its cycle. Without the phases, the pattern was just,
Right.
well, a pattern,
Yeah.
uninterpretable in 3D. It was the infamous phase problem.
Like having the volume levels for an orchestra, but not knowing when each instrument starts playing, you can't reconstruct the music.
That's a great analogy. Exactly that. So the data was there, locked away in the pattern, but the key, the phases, was missing.
So faced with this massive challenge, how do they even decide which protein to start with? Must have seemed impossible.
They needed a strategic target. Something complex, yes, but hopefully just maybe manageable. And they chose myoglobin.
Myoglobin. Muscle protein stores oxygen. And famous for being abundant in diving mammals, right? Whales, seals.
That's the one. And yeah, the source material notes they got it from whale meat. Definitely not your standard lab chemical order back then,
A bit unusual, yeah.
but a smart choice. Myoglobin's relatively small, about 17,000 molecular weight. Compare that to hemoglobin, the oxygen carrier in blood, which is much bigger, around 67,000.
Okay, so smaller is better here.
Generally, yes. easier to crystallize, fewer atoms to map. And myoglobin only has one heme group, the part that binds oxygen, whereas hemoglobin has 4. Fewer moving parts, in a sense. About 152 amino acids, still incredibly complex, but it felt like the right scale of challenge.
Got it. So myoglobin it is. They have the X-rays, they have the protein, but they still have this giant phase problem staring them down. This is where the genius comes in, right? How did they crack it?
This is where Max Protz's pioneering idea, refined and really driven home by John Kendrew's team on myoglobin, comes into play. Isomorphous replacement.
Isomorphous replacement. Okay, sounds technical. Break that down for us.
Okay, think about it like this. You have a blurry picture, and you want to figure out the details. What if you could add a couple of really bright, known reference points into the scene?
Like adding bright stars to a fuzzy nebula image? Sort of, yeah. They took their myoglobin crystals and carefully soaked them in solutions containing atoms of heavy metals, mercury, cadmium, things like that. These atoms are electron dense, so they scatter X-rays really strongly compared to the carbon, nitrogen, oxygen atoms of the protein.
Okay, so they add these heavy atoms.
And the crucial part is isomorphous. They had to get these heavy atoms to bind to the same specific spot on every myoglobin molecule within the crystal without messing up the protein structure or how the crystals pack together. That was incredibly tricky.
Right, can't distort the very thing you're trying to image.
Exactly. But if they succeeded, that strongly scattering heavy atom would cause subtle but measurable changes in the diffraction pattern compared to the pattern from the original crystal without the heavy atom.
Ah, I think I get it. So you compare the before picture, native crystal, with the after picture, crystal with heavy atom. And because you know where you put the heavy atom and how much it scatters, you can work backwards to figure out the phases for the protein itself. That's the core idea. It's like knowing the total sound and subtracting the sound of the trumpet you just added to figure out the sound of the rest of the orchestra. They needed to do this not just once, but with several different heavy atom types, each hopefully binding to a different spot on the protein.
Wow. Finding those heavy atoms that worked and didn't wreck the crystal must have been painstaking.
Oh, it was years of intense chemical work, trial and error, screening different compounds. And that's not even mentioning the challenge of just getting good crystals in the first place.
Right. Protein crystals are notoriously fiddly, aren't they?
Extremely. Fragile, hard to grow large enough, stable enough. They had to develop new techniques, like crystallizing at low temperatures, using tiny seed crystals to get things started. It all relied on having these beautiful, well-ordered crystals.
Okay, so let's assume they managed all that. Good crystals, working heavy atoms, the isomorphous replacement strategy. What's next? Collecting the data.
Yes. And this is where you just have to appreciate the sheer human effort involved. No automation. They had to collect diffraction data, measure the intensity of thousands of spots on photographic films for the native crystal and for each different heavy atom derivative crystal.
Thousands of spots on film.
Which then had to be developed. And then someone had to sit there with a device called a densitometer and manually measure the darkness, the intensity of every single one of those thousands of spots for every film.
Manually.
The paper itself mentions calculating electron density values at 500,000 grid points. Imagine the meticulous, repetitive work, measuring tiny spots, recording numbers day in, day out, years of it.
500,000 points by hand. Wow.
It's astonishing perseverance. And all that raw intensity data combined with the phase information they painstakingly derived using the heavy atom comparisons finally allowed them to calculate an electron density map.
Okay, the map.
Yeah.
What did that look like?
Think of it like a 3D weather map, but showing where the electrons are densest in the molecule. At 6 angstrom resolution, which is not super sharp, you can't see individual atoms clearly.
An angstrom being tiny, like atom-sized.
Yeah, about the size of a hydrogen atom. So 6A is, well, blurry, but it was enough. It showed these continuous regions of higher electron density, tracing the path of the protein's backbone.
So they had this blurry 3D contour map. How do you go from that to an actual model of the protein chain twisting and turning?
This is another amazing part. They literally built it by hand. They printed out sections of the electron density map at different levels, like slices through the molecule.
Like a stack of topographic maps.
Exactly. And they'd look at these maps and trace where the dense sausages of electron density ran. Then they physically built a model, using wire or rods, carefully bending and connecting them to follow those density contours in 3D space.
They were sculpting the protein based on the X-ray data.
Pretty much. A physical manifestation of the calculated electron density. It was literally the first time anyone had ever seen the complete folded path of a globular protein chain.
Incredible. And who was doing this? Was it a massive team?
Actually, no. That's part of the story's charm, in a way. It was a relatively small group. 6 authors on the paper, led by John Kendrew, working closely with Max Perot's hemoglobin group, all within the same MRC unit at the Cavendish lab in Cambridge.
So not some huge factory.
Not at all. It was this model of a small, dedicated team with diverse skills: crystallography, physics from Kendrew, chemistry, model building, tackling a massive problem with incredibly long-term commitment. And the sources mentioned how important internal critique was. People like D. Phillips challenging the interpretations, making sure the model fit the data. That intense collaboration was key.
Wow. Okay, so after all those years, all that painstaking work, the manual measurements, the chemistry, building this model literally by hand from a fuzzy map, what was the big reveal? What did myoglobin look like?
It was revolutionary. The model showed a compact, kind of sausage-shaped molecule overall, which made sense for soluble protein. But the inside, it wasn't random at all. It was dominated by alpha-helices.
Those spiral structures Pauling predicted.
Exactly. They could clearly trace about 8 distinct alpha-helical segments. These weren't just floating around. They were packed together in a very specific, intricate way, connected by shorter turns, all cradling that central heme group.
So the helices weren't just in fibrous proteins, they were major building blocks here too.
Yes. And crucially, they were arranged in a unique, complex, but ordered tertiary structure. This was the first definitive proof that these globular proteins folded into specific, predictable 3D shapes. It showed the amino acid sequence dictates a unique fold.
Which completely flew in the face of the random coil idea.
Completely. Yeah. It demonstrated that these molecules had precise architecture. And this wasn't just academically interesting. It was the first time scientists had a concrete physical framework to understand how a protein actually works. You could literally see how the chain folded to create the pocket for the heme group, the site for oxygen binding.
Function finally had a physical basis you could point to.
Precisely. Structure explains function. This was the first atomic-level glimpse of that principle in action for a globular protein.
Did they double-check this? How did they know the model was right?
Yeah, they were rigorous. They didn't just rely on the X-ray map. They used other techniques. For instance, they could predict certain properties, like how the protein should absorb light based on their model, and then compare those predictions to actual experimental measurements on myoglobin solutions.
Checking the model against reality.
Exactly. Things like shift-based different spectra, apparently. It helped rule out alternative, simpler models, like just packing spheres together. The complex helical structure they built was the one that best explained all the data, not just the X-ray map.
Okay, so it was solid, groundbreaking. Let's talk about the impact. This wasn't just about understanding myoglobin, was it? It sounds like it kicked off a whole new era.
Oh, absolutely. The ripples were enormous, both theoretically and technically. Theoretically, like we said, it just fundamentally changed how scientists conceived of proteins. They weren't amorphous blobs. They were intricate molecular machines with defined structures determined by their sequence.
Proving that stable, folded 3D structures were real for these globular proteins.
Right, and technically it was huge. The method they used, multi-isomorphous replacement, MIR, became the workhorse technique for solving protein structures for decades. It gave everyone the key to unlock the phase problem.
The method itself was a major innovation.
Foundational. It enabled scientists to determine the structures of thousands upon thousands of other proteins, pushing to higher and higher resolutions. It also really highlighted the need for ways to store and share this structural data, contributing to the eventual creation of the Protein Data Bank, the PDB, which is essential today.
So it gave us the method and started the library.
You can say that, yeah. And it directly enabled Perot's and his team to solve the structure of hemoglobin, soon after bigger, more complex, but building directly on the myoglobin success. But maybe the biggest ripple effect for many people, it paved the way for rational drug design.
Rational drug design, that sounds important. Explain that connection.
Okay, so before this, finding new drugs was mostly trial and error. You'd screen thousands of chemicals hoping one would stick, often without knowing why it worked.
Throwing darts in the dark.
Pretty much. But once you know the precise 3D structure of your target protein, say a crucial enzyme in a bacteria, or a receptor on a cancer cell, you can see its shape. You can see the pockets and grooves on its surface.
Right.
And then you can start to rationally design small molecules, potential drugs, that are shaped to fit perfectly into those pockets and block the protein's function, or modify it in a desired way.
Designing a key for a specific lock, because now you can see the lock.
Exactly that. This myoglobin structure was the dawn of that whole approach. It shifted biology and medicine towards thinking about molecular interactions in 3D. Even though the 60-ohm resolution wasn't atom perfect, it proves the concept. It showed these defined structures existed and could, in principle, be mapped. It was the start of the molecular structure era, a true paradigm shift.
So we've journeyed back to 1958, explored whale meat crystals, heavy atoms, hand-built models. But let's connect it to now. Why should this discovery, over 60 years old, about one specific muscle protein matter to you listening today?
Because honestly, almost everything we understand about how life works at the molecular level builds on this foundation. Every time you hear about how an enzyme speeds up a reaction, how an antibody targets a virus, how your cells communicate, how DNA gets copied, even how a specific medicine works by hitting its target,
Yeah.
all of that understanding relies on the fundamental principle established right here. The proteins have specific, intricate 3D shapes, and those shapes determine what they do. This work unlocked our ability to see and understand that molecular world.
It's the origin story for so much of modern biology and medicine. It proves shape is king at the molecular level.
It really did. It's when biology started looking less like just complicated chemistry and more like, well, nanotechnology designed by evolution with parts that have specific forms we can actually figure out.
What an amazing achievement. Going from those vague blob ideas to revealing this precise, almost artistic structure inside myoglobin. Just incredible scientific persistence and creativity.
Absolutely. And it leaves us with a fascinating thought, doesn't it? If just getting that first blurry 3D picture of one protein could revolutionize biology and lead to things like rational drug design, what are the next fundamental sites we need in biology?
Meaning,
Well, what are today's difficult to analyze blobs? What complex systems, maybe interactions between many molecules or processes happening inside cells, are we still struggling to visualize properly? What new way of seeing might unlock the next wave of breakthroughs, just like seeing myoglobin structure did back then?
what's the next myoglobin moment waiting to happen? Something to definitely ponder.